Okay, so we're going to try this again. This is acid-base properties of salt solutions. I'm going to go through this fairly fast here, if I can. So basically, what we're talking about here is that when you put a salt solution into water, it can be an acid or it can be a base, depending on how it dissociates. Okay, so you got to remember that when you put a salt into water, it is going to dissociate. That's an ionic compound. Typically, ionic compounds dissociate unless they are insoluble in water. Okay, so we're going to talk mainly about the ones that are soluble in water. And the assumption that we're making here again is that when the salts do dissolve, then they completely dissociate, because ionic compounds do that. So the ions formed when the salt dissociates, they can react with the water sometimes, to form H plus or OH minus. Okay, and that's called hydrolysis. We talked about hydrolysis earlier in the year. Hydrolysis is actually kind of the opposite of an acid-base reaction. Like, let's see, the one that we talked about a lot last year was not last year, but earlier this year, NaOH plus HCl reaction. Okay, when that reacts, it forms NaCl, a salt, and H2O. Okay, so this is kind of the opposite of that. You can sort of think of it that way, in the sense that we're starting with the salt and with water. Okay, and then what we end up with is we end up with an acid or a base. Okay, and so that's the idea with hydrolysis. Okay, so most of the time when you have an anion, it's negatively charged, so it makes sense that what it's going to do is actually take a hydrogen from water, because then it will sort of help it to have less of a charge. The negatively charged thing is going to be more attracted to the positively charged hydrogen. So the negative ions in the salts typically are the ones that act like bases. Okay. Now here's the thing: if X minus is the conjugate base of a strong acid, it's not going to affect the pH. So here's an example. If we have Cl minus in solution, so if we think about this, if you got Cl minus and you add it to H2O, okay, then what this should do, if it took a hydrogen from the water, then it would make HCl and OH minus. Okay. Well, problem with that is that HCl, we know, always dissociates in water. It's a strong acid, right? So that HCl, that H from the water, is never going to come back together with the Cl minus to form HCl. Okay, so that just doesn't happen. So basically, this is a no reaction here. Okay, that doesn't work. All right. Now, if X minus is the conjugate base of a weak acid, then that actually can happen. Okay, an example of that is the acetate in solution. So you've got C2H3O2 minus. When that combines with H2O, you're going to end up with C2H3O2 plus OH minus. Okay, and that actually can happen because acetic acid is a weak acid, so it doesn't completely dissociate, which means that most of it stays together. Okay, so that actually can happen. So you got to keep those two straight. If you have an anion that forms a strong base, then it's not going to do anything to the pH of the solution, because it will not pull a hydrogen off of water. But if it forms I said a strong base, I meant a strong acid, like HCl. But if you have an anion that forms a weak acid, that can actually happen, okay? All right. If X minus is an anion with an ionizable proton, it could be amphoteric, okay? So then you have to compare the Kas of these two things. So an example here would be HSO3 minus. So if you got HSO3 minus, this could do one of two things, okay? It could I'll put it with water both times here. So it could react with water and act like an acid, give away its hydrogens, then you'd end up with SO3 2 minus plus H3O plus, right? Or the other thing it could do is it could react with the water and go the other direction here, where it actually takes a hydrogen from the water, and then it makes OH minus and H2SO3. Okay? So either one of those could actually happen. So then what we have to do to figure out which one of these is going to happen the majority of the time in the solution is we got to look at the Kas for those. So I actually need to look that up really quick because I didn't have it in front of me. Let's see. So the Ka for, well, see, this is tricky because what the book gives us is the Ka for H2SO3 is 1.7 times 10 to the negative second. And then the Ka for HSO3 minus, if it still acts like an acid, that's going to be 6.4 times 10 to the negative 8th. Okay, now the problem here is that for one of these we don't need the Ka, we actually need the Kb. Alright, because the top equation here, or sorry, the bottom equation is acting, the HSO3 minus is acting like a base, okay? And so what we need here, if you notice this HSO3 minus equation on the bottom here, this one is the kind of the opposite of the acid equation for H2SO3. Okay, so what we have to do is use our Ka times Kb equals Kw thing, and we can find the Kb for this bottom one, okay? Now the Ka for this top one here, you already know that, 6.4 times 10 to the negative 8th. The Kb down here, once you plug that into the equation here, you're going to end up taking 1 times 10 to the negative 14th divided by 1.7 times 10 to the negative second. And that's going to give you a Kb of 5.88 times 10 to the, I don't know why it's messing up like this, times 10 to the negative 13th. I think I have a short or something in this. Okay, so that's the idea on that one. Now, once we compare those two, notice that Ka number is quite a bit bigger than the Kb number, which means that this one is going to happen quite a bit more often than the bottom one, okay? So that means the majority of this, and when you put this into the HSO3 minus into water, then that's going to act like an acid more often than it acts like a base, so that's going to make an acidic solution, okay? Alright, polyatomic cations. If it has more than one proton in the formula, it can be considered the conjugate acid of a weak base. Now, the only example of this that we ever really talk about in AP Chem is NH4+, okay? There are other polyatomic cations, but this is the only one that we've really talked about. So, NH4+ has 4 hydrogens in it, okay? So it seems fairly simple for that NH4+ then, when it reacts with water, to give away a hydrogen to the water, make NH3 plus H3O plus, right? So you just have to remember that with the NH4+, that actually is it's gonna act like an acid, okay? And then, you know, aside from that, most of the time the cations that we have in our salts are going to be metals, okay? And so metal ions are typically going to react with water to decrease the pH of the solution. I said that we'll talk about how this works later in the year, We've already talked about that, though, when we talked about Lewis acids and bases. And remember, a lot of transition metals especially can act as Lewis acids, which means they are electron pair acceptors. And when they do that, they can actually reduce the pH of the solution, okay? When they interact with water in that particular way. So just remember that most metals, most transition metals, and most some other metals as well will decrease the pH of the solution when you put them into water, okay? That's what you mainly need to remember there. Now, the exception here is the ions, the alkali metals, and the heavy alkaline earth metals. When I say heavy, I mean calcium, strontium, barium, radium, okay? Those are the heavy ones. Those are the ones that don't affect the pH of water. They're not going to react with water at all, okay? And so you just kind of have to remember that. I mean, the alkali metals are kind of the alkali metal ions, I should say, are kind of the lazy ions on the periodic table. They really don't do much of anything in water. They don't precipitate with anything, and they don't change the pH of the solution. They don't react with the water, okay? All right. If the anion and the cation, so now we're going to try and predict the pH when we put these salts into water. So you got to think about a few different scenarios that could happen. If you got the anion and the cation, and both of them are unreactive with water, that's a neutral pH because they're not producing any H plus or any OH minus in that case, okay? If the anions react with water, or if the anion does and the cation doesn't, that's going to make the pH high, because remember, the anion is the one that's going to tend to form a base when it reacts with water. So if the anion reacts and the cation doesn't, pH is going to be high. If the cation reacts with water and the anion doesn't, then it's going to be acidic, okay? Now, where it gets a little more complicated is if they both react, okay? Then you're going to produce hydroxide and hydronium, and so then you have to look at the equilibrium constant for each of the ions and figure out what the pH of the solution would be, okay? So the ion that has the largest equilibrium constant is going to have the greatest influence on the pH. So you just have to check that. Any question that asks you about that is going to give you the K for each of those, and then you just have to compare the two, okay? All right, so the sample problem here, predict whether the salt Na2HPO4 will form an acidic or a basic solution based on dissolving in water. Okay, so we're going to put the Na2HPO4 into water, and as soon as we do, this is going to dissociate, right? So you're going to have Na plus and HPO4 2 minus, because there's two sodium ions here, okay? And so you're going to end up with HPO4 2 minus. Now, the sodium we know does nothing in water, it doesn't react, okay? So we can just ignore that. So really, the HPO4 2 minus could do one of two things here, okay? It could either act as an acid to form H plus and PO4 3 minus, or it could act as a base and make H2PO4 minus and OH minus, okay? So either one of those things could happen because HPO4 2 minus is amphoteric. It could either gain a hydrogen or it could lose one. So what we have to do again is we need to know the Ka's for both of these things, or I guess the K for one, the KB for the other. This top one here, so what we have data for in the book is we have the H3PO4, the Ka for that one is 7.5 times 10 to the negative third. The Ka for H2PO4 minus is 6.2 times 10 to the negative eighth. And the Ka for HPO4 2 minus is equal to 4.2 times 10 to the negative 13th. Okay, so there's all of our Kas. Now we're going to have to figure out how to translate that into a Kb for the bottom one. But this top one here, that is our Ka, 4.2 times 10 to the negative 13th. Okay, again, a very, very low Ka there. Now the HPO42 minus, that's actually going to be the conjugate base for H2PO4 minus. So the Ka for H2PO4 minus we have right here. Okay, so we need to actually use the Ka times Kb equals Kw equation for that one. So 1 times 10 to the negative 14th divided by this number, 6.2 times 10 to the negative 8th. That gives us a Kb of 1.6 times 10 to the negative 7th. Okay? So obviously, the bottom one has the bigger K. So this bottom equation is the one that's going to predominate when we put it in that solution. Okay, and so this isn't going to end up being a basic solution. Okay, now, just to say this, make sure that we know here, these are both going to happen in this solution. Okay, both of these reactions are going to occur, but the bottom one is going to occur much more often, which means that more OH minus is going to be produced than H plus or H3O plus. Okay. All right. Predict whether the salt K2HC6H5O7 will form an acidic or basic solution in water. I'm going to skip that example because it's basically just like the last one. Because again, when you put this into water, you end up with K plus, 2 of them, and the HC6H5O7 2 minus, okay? And so then what you'd have to do is figure out, is this going to give away a hydrogen in water, or is it going to take a hydrogen in water? It could do either one, so you need to figure out which one it's going to be more likely to do, okay? So really, same basic thing as what we did on the last one, so I think you can probably work that through. All right, last example here. List the following solutions in order of increasing acidity or decreasing pH. Okay, so the first thing I would do is just walk through all of these and figure out, is it going to be an acid solution or is it going to be a basic solution? Okay, so the first one here, BaC2H3O22, that is going to be, well, first of all, barium is one of those heavy alkaline earth metals, so it does nothing when you put it in water. It doesn't react with the water, okay? So then we've got C2H3O2, which is a 2 minus when this dissociates. So this one right here is actually going to end up being basic, okay? Because our anion will react with the water, but our cation won't. Because if you think about it, C2H3O2, whoa, sorry, O2, 2 minus. When that reacts with water, it's going to make HC2 H3O2. Oh wait, I'm sorry. That's a 1 minus. Okay, so HC2H3O2, which is a weak acid plus OH minus. Okay, so that will actually form a basic solution because this is a weak acid over here, so that will happen. Okay. By the way, another thing, a good question that was asked on this the other day. This acetic acid right here that gets formed, it looks like an acid and a base get formed here, and that is true, but it's a weak acid and a strong base, okay? So that OH minus, that is a strong base. That's kind of the definition of a base. This HC2H3O2 that gets formed, only a little of that is going to, dissociate and form H+. So there will be a little bit of H+ in that solution, but overall it's going to be a basic solution because there's OH- in that solution. Okay. Alright, so the second one here, the NH4Cl. Well, the Cl- we know is not going to do anything in water, because if it did, it would, when it took a hydrogen away from water, it would form HCl. That's a strong acid. Okay, so that's not going to happen. The NH4+, we've already talked about the fact that that is going to form an acid. Okay, so this one right here is going to be acidic. Alright, next one down, NH3CH3Br. Once again, well, okay, first of all, and this confused me the first time I went through it, but this is going to dissociate into Br minus, and I should erase this other stuff so you can see what I'm doing here, and NH3CH3 plus. Okay, so when that dissociates, this NH3CH3 plus seems like a good candidate for maybe giving away a hydrogen. So this is an example of one of those polyatomic ions that we haven't really talked about. But this one would give away a hydrogen, and when it does, it would form NH2CH3. Okay, and so that's going to be also acidic when you put it into solution, because it's going to give away a hydrogen, and the anion doesn't react. By the way, the Br minus, I don't think I mentioned this, but the Br minus won't react, because if it did, it would be taking a hydrogen from water, forming HBr, but that's a strong acid, so that can't happen. Okay. Then the KNO3, I don't know why that line is there, I can't get rid of it, but the KNO3, potassium is an alkali metal, so that's not going to do anything in the solution. NO3 minus, if it reacted with water, it would form HNO3, which is nitric acid. HNO3 is also a strong acid, so the NO3 is not going to react with the water either. Okay, so this one right here, the KNO3, cation and anion, neither one react, so this is just going to be neutral. Okay, so now we have a general idea of our order. Okay, we want to do this in terms of increasing acidity. Okay, so that's going to be, obviously our last two will be the NH4Cl and the NH3CH3Br. The basic one, that would be first, so let's go ahead and list these here. Ba, hang on just 1 second here. Okay, sorry, so the last thing we need to talk about here, sorry, I was actually putting these in order, and I lost everything that I was writing on here, but hopefully that all made sense from before. So the basic one, again, is the BaC to H3O2, 2. So that would be the first one on our list, because that's the basic one. Why is this doing this? Then we would have to put the neutral one next. Okay, that'd be the it's ridiculous. And now it's not erasing it. The KNO3 would be next. Okay, and then we'd put our two acids. Now, what we would have to know here, we'd have to know the Ka for the NH4 plus versus the Ka for the NH3CH3. Okay, so let me see if I have the Ka for the NH3CH3 plus. That one I'm probably gonna have to look in the back of the book for, because it's not in the front of the book. Give me 1 second, and then I'll tell you how you can answer this part. Should have done this while the video was still paused. Okay. CH3 and H2, the methylamine. Okay, I have the Kb for that one, so which is 4.4 times 10 to the negative fourth. So the Ka for the NH3CH3 plus is going to be 2.27 times 10 to the negative 11th. All right. Which is, you know, a fairly large Ka, or fairly small Ka, sorry. And then the Ka for ammonium is, I'm having to convert this one too, 5.6 times 10 to the negative 10th. Okay, so then we can compare those two Kas and see that the NH4 plus has a little bit bigger Ka, not much, but a little bit bigger Ka. So that one is actually going to be a little more acidic. So that's going to be our last one on the list. So that means the NH, good grief, sorry, I'm not aiming well. So that means the NH3CH3Br is going to be next on the list, and then the NH4Cl will be last, the most acidic. Okay? So that's how you would do that. You'd have to have Ka values for this to work. So, alright, that's it for today. I'll see you guys in class.